Hi, this is Thomas. We are group number 6. Today I'm going to present you our project on the Kaggle competition PetFinder.my popularity contest. So this is our table of contents. First, we will go through the background. Then in the EDA section, we will show you some insights. Then moving on, we will have a section about evaluation metric and loss functions. Then the next part will be about data preprocessing. Then training, evaluation, and then give you a little bit on the conclusion and some extra work that we could do in the future. So moving on to the dataset, we are given the popularity score as the target. And the popularity score, according to the competition host, they say it is based on the pet profile page views on their website. In total, there are 9,913 training images of cats and dogs. We are also given the metadata of images, and those metadata are fields that describe the images. And if you're interested, you can look at the table on the right side, but we are not going to go through them because there are too many. So additionally, to further improve our model performance, we are going to use two external datasets. So one is the PetFinder.my adoption prediction competition dataset, which is basically their previous competition. And another one is the dogs versus cats competition dataset. So a little bit on the submission rules because this is a competition. So the competition only allowed Kaggle notebook submission, and the test sets has about 6,000 images. It is also hidden, and it is only used to score our submitted Kaggle notebook. There's another concern about the notebook runtime. So the notebook runtime is limited to 9 hours max. So for EDA, there are some images that includes multiple pets, so like the one on the right side. And there are also some images includes pets that are partly blocked by objects, such as fences and cages. And images are of different sizes and also different aspect ratios, and most of them are not in square.
In this competition, all the submissions will be evaluated by root mean square error at the end of the competition. And here is the distribution of the target values. You can see they are positive integer within 0 and 100. And most of them actually are not close to 0 or 100. They are mostly clustered between 20 and 30. Although the competition is a regression task, normally we should use the MSE loss. But people in the forum discovered that actually binary cost entropy loss performs better in this case. People don't know why, but to my understanding, based on the distribution plot in the previous slide, you can see most of the target value, they're not close to 0 or 1. If you look at the chart on the bottom right corner in this slide, you can see if the target value is 0.4, right? If you have a prediction that's close to 0 or 1, the loss is super high for BCE and even higher than the MSE loss. So we can consider that BCE loss will penalize heavily for prediction that is close to 0 and 1, right, when the target value is not close to 0 and 1. So other than BCE loss, we also discovered that KL divergence loss is useful. Similarly, it is a classification loss, but if you look at the chart on the bottom left corner, both BCE and KLD loss produce a training process that is slightly better than the MSE loss, but they actually converge to different locations. So at the end, we will use these three functions to train models variance for the ensemble learning purpose.
Let's talk about the data cleansing part. The data cleansing steps always is the most important part to maintain the image consistency. The dimension controlling can help to avoid the distortions, which can give us a very huge performance boost. Most of the computer vision models inputs are optimized the input layers in square. While according to our EDA, most of the images in this competition are not squared, since most of them are taken by the mobile phone. In these cases, cropping and padding provide us a very great solution. In the dataset, we observe there are two types of images, one pad or group of pads, which lead to different pre-processed methods. For one pad, we will crop it directly, and on the other hand, for the group of pads, we can't crop it, so we add the padding to the shorter side to reform it into a square. For the data augmentation, there are several augmentation methods to generate more data to train a model. The augmentations always include resizing, positional shifting, orientation scaling, and some color changing. At the beginning, the input image will randomly crop into different scales. Next, we will apply the either horizontal flipping and perspective shifting. Then we will randomly apply one image processing algo from the following: Gaussian blur, color jitter, and the random augmentation. Random augmentation is an adjustment bundle which randomly picks three functions along contrast stretching, equalizing, sharpening, and solarize enhancement. After all, we will normalize the image by RGB channel using the ImageNet means and standard deviation as the model input, which can help us to converge the model rapidly. According to the CNN architecture, the input image will be convoluted a few times to create a receptor field that we call RF. To compare the CNN with the transformer-based model, the RF showed its bottleneck since it's too narrow to present the raw image. As we can see from the left-hand side, the outputs of the last convolution layers can only present the parts of the pixel from the original image. There on the left-hand side, that's the transformer can measure the object-to-object connection using the query and the key to do the connection from the images. In past few years, computer vision model is migrating from CNN to the transformer. In 2020, third, an end-to-end transformer detector has been proposed and proven to perform well on the Kaggle and ImageNet datasets. And with the vision transformer, it split the image into the patches, which provide an easier way to query and interpret the relationship between the objects using the relative geometry features. But width has its locally limitations, which does not have any linkage between patches. So Swin come out and propose the shifting window to solve the patches connection issues. In computer vision, visual signals are highly coordinated in spatial. Locality information is always an important factor in modeling. We split the image into many patches, but it leads to a lack of communication between the windows. Shifting window is the key concept of Swin for cross-window connection. The shifting windows concept is similar to shift the convolution kernels with the straight equal to 2 through the image and learned attention mask, while it doesn't need to spend extra cost to create a new kernel.
Let's talk about model architecture. Our training pipeline can be roughly divided into two stages. Within each cost validation fold, the competition data will be classified into dog or cat images. This is done by a dog or cat classifier. The classifier was trained on two external datasets. The reason is that we don't have dog or cat information in the existing current competition dataset. So we need to use two external datasets to train a dog or cat classifier. The two external datasets are the previous PetFinder dataset and the other dedicated dog or cat dataset. So we are able to get a dog or cat classifier with over 99% accuracy on a balanced validation set. Next, we are going to train models for predicting the competition target. We train separate models for cat and dog images, but their configurations are the same. For the purpose of ensemble learning, we include the following variants. First, we include different input image size of the pre-trained Swin Transformer models. And we also train the models with different loss function, including the MSD loss, the BCE loss, and also the KL divergence loss. So at the end, the predictions of different models are aggregated by a simple averaging to produce the final predictions. To train the transformers described above, we use the following training and fine-tuning procedure. In terms of computation resource, we use mixed precision training to lower the GPU memory usage. Even though we use mixed precision training, we still cannot afford to have a large enough batch size. To fix this issue, we use gradient accumulation, which we can use this to have a larger effective batch size. In terms of fine-tuning, we firstly freeze the pre-trained image model, and train the newly added fully connected layer first to warm up it to avoid the effect of random weight initialization. So after training a few epochs, we unfreeze the pre-trained model and fine-tune the entire model end-to-end. It has been discussed that transformer is harder to train and suffer from convergence issue. It requires careful design optimizer and learning weight schedulers. The community usually suggests us to use Adam Dub optimizer and also the cosine with warm-up learning weight scheduler from Hugging Face This learning weight scheduler produces a super low learning weight at first and then slowly increase the value to the base learning weight. And after this, it follows the cosine learning weight pattern. So we use this procedure to smoothen the training process of the unfazed transformer model. To sum up, we firstly train 10 epochs with the P-train transformer phase at a constant learning rate to warm up the fully connected layers. Next, the model is trained for another 10 epochs with the P-train model unfazed, but the learning rate now is a super low and rising learning rate. It is to warm up the Swin transformer. Finally, the whole model is trained on a cosine learning rate schedule with a 20 epoch cycle.
So for evaluation, we are using 5-fold cross-validation. Each fold has 2 sets of ensemble models, one for cats and one for dogs. So the local validation RMSE is 17.15, and the public leaderboard RMSE is 17.77. So to further understand that if our model is actually learning from the images, we have actually visualized the activation values of our Swin backbone using GradCam++. We can see that the images on the right, there are high activation values around pets. So basically those areas that are blue represents a high activation value. We can also see that for images with multiple pets, the model is actually focusing on each of them. We can see that it is not perfect. The contour or the outline of the activation value is not perfectly on the pet. Sometimes it is focusing on other areas a little bit off from the pet. So it could be indicating that the pet's appearance is not the only factor of its popularity. So in conclusion, on what we have done so far, we used a 2-stage method to score the cats and dogs images. Then we also use the Swin transformer as our backbone, and then we ensemble multiple of them with different losses to achieve a better score. We have also used GradCam++ to display the activation values of our Swin transformers on the images. We found that it is actually focusing on the pets, which is amazing. So there are 4 possible ways to improve our model. So the first one is that we are thinking to use not only Swin as our backbone, but also ensemble our model with CNN models. And secondly, we can use a more advanced cropping technique, such as using a Swin detector or a YOLO model to crop the identified pet to make sure we are not cropping out parts of the pets. For images with multiple pets, it is very easy to identify them because we are given the metadata. And for those images, we can crop each pet as a separate image, and then we can predict on the image independently. Then we can average out the predict as our final prediction. Last but not least, we can try to use the Swin Transformer version 2 that has just been published, and we believe that might help a little bit to further improve our RMSE. So this is the end of our presentation. Thank you.